2 teams at least already that I am aware of. Let's see who are the others. So first of all, pushback pioneers, can you raise your hands? Yeah, okay. Good. Team right wing. Okay. So everybody is towards the right. Okay. Turbulence squad. Oh, nice. Okay. No wonder you are secretive about it so far. Okay. Who are in your team? Turbulence squad. Raise your hands. 1, 2, 3, 4, 5, 6, 7, 8. We are allowing up to 8, right? That's the maximum. Okay. Any other teams? Blackbird. Okay. How many of you? Okay. Good. Garud. Okay. Nice. Okay. So we have 3 plus 2, 5 teams already in place. One more. Okay. Anybody who has just come in, part of any team? So any teams other than what we have already heard so far? We've heard of 5 teams so far. Those who are not part of any of these 5 teams, we still don't have a team. Okay. Just the 2 of you. Anybody else? Everybody else is in a team. But we had totally 38, right? Students? 40. Okay. So we have 40. Can you just count in terms of the numbers that we already have in teams? Pushback pioneer, how many of you? 6. Pushback pioneers? 7. 7. Yeah. Then team right wing, how many of you? 6. Turbulence squad? 8. Blackbird? 5. Garud, yeah. Team Garud, how many? 8. So how many you have total? 32. That leaves the remaining to be in one group. All right.
How many have registered?
Probably on the 20th, I'll know for sure. Yeah. Apart from the 2 of you, anybody else who is not yet in any team? Okay, can you just group whoever is not there so that you have one team? Yeah. Yeah.
Instead of these 2 being 8, which is slightly on the higher stage.
Okay.
2 of them and anyone who is joining later, we give 1 more week time, like not for presentation, but we take them up on board for that group. Otherwise, this 4 will become a group for us actually. Removing this, and this will become 6 instead of 8.
You mean you want to split this?
Split. Give them only 6 people whom they want. They are no problem in sacrificing. 2. Sacrificing 2 here, and the remaining who will join in between. So that will become 5 members, and that will also become 1 group. So we have 6 topics and 6 groups.
Have named themselves ready to present. Yeah, about you guys. Yeah, your team. You guys are ready to present? Okay, but you're all ready to present today, right?
Yes, sir.
Yeah, Garud? Okay, so that's good. Really happy to see at least 80% of the students already grouped themselves and also ready to present today. But I have a kinder set of teaching assistants than I expected, especially the group captain from the Indian Air Force, much kinder. Of course, we are familiar with Air Force officers from Hollywood, Bollywood movies, but what goes behind that in terms of whatever they do, the tough things that they do, is a kind heart. And so he has recommended that we shift today's presentation to Wednesday. So you get 2 additional days to prepare. So those of you are already there and want to go today, I'm sure there's always a room for improvement. So utilize the next 2 days to improve upon your presentations. And this gives time for the 8 who have not yet grouped to form a group, identify who else is not in any group, and then you form your group. Okay, so it's important. So talk to them and make sure by the end of this class you're already in a group of 5 to 8. Okay, any questions or doubts about the projects and the presentations? Because from Wednesday onwards, even if they recommend, I'm not going to postpone anything. Every Wednesday we'll have, because we have 13 weeks including this week, so we have 13 topics, and every Wednesday at the beginning of the class there will be a presentation by the 6 groups, and then we will move on to the class depending upon how much time we have left. Okay, try to stick to your time duration that is allotted for the presentations, 10 minutes. So don't overshoot that, so that we try to finish it in about 1.5 hours, including the question and answer session. Right? We will have a total of half an hour of question and answers and also 1 hour of the actual presentations. No more postponement for the individual report submissions as well, which go along with the group report. So on Wednesday, we would like to have your first presentation as well as all the team's reports, which include the 5 to 8 individual reports depending upon the strength of your team. Right? That being the case, today we'll have a regular class, and from day after tomorrow onwards, every Wednesday we'll have this presentation in a sequence. Some Wednesday happens to be a holiday, then probably we'll have to shift it either to a Monday or a Friday. We will decide based on that, right? Most probably we'll shift it to the Friday so that you still have some time to work over it. I'm not sure if there's any Wednesday which is a holiday anyway. We'll check that. In any case, day after tomorrow, you definitely will have your presentations. One of the things that I've mentioned probably repeatedly, and also wouldn't mind stressing it again, even if it sounds boring, is that any new subject that is there, half the subject is learned once the terminology is learned. Today, a lot of what we'll be doing is essentially to understand that terminology so that it brings a level playing ground between those of you with a non-aerospace background and those with an aerospace background as far as undergraduate program is concerned. Because once you know a lot of these terms and you familiarize yourself with that a little more, then you see that most of the distinction. Okay. Sure. Is that fine for most of you? Yeah. Okay. Good. So maybe you could shift to the next table. Yeah, that's on. Yeah. Camera. So that it's kind of normal to the. I think all of you have got these white sheets with you. Don't worry, no exams over here, even though it looks very similar to your exam sheets, the extra sheets that you get when you write your exams. I want all of you to go back to your childhood days and recollect how you made paper airplanes to make a paper airplane out of the first paper that you have with you. If something goes wrong, gets messed up, you can use the other sheet, and if you need more, we have plenty of supply over here, but try to be kind to the trees and the forest. The reason why you're making this is it's not competitive. I don't want you to maximize the range or endurance or whatever. Just make something which kind of looks like an airplane, at least convinces you, if not others. So what you will have eventually is something that you can play around with while I kind of demonstrate with a toy over here as well. Better in terms of the scale, so that at least the people at the back can recognize what we are looking at and what we are talking about in the class, right? So then, because that is kind of part of getting used to the terminology, it's not just about writing on the board the equations, that the symbols that we use for various terms, etc. That anyway we will do. It's part of the main understanding from an engineering scientific point of view. But nonetheless, if we have a hang of what we are physically referring to, then it makes much more sense in terms of those equations. They get better understood. So keeping that in mind, let's get back to something that we have talked about earlier, but here it's put up in a more pictorial sense in terms of many of the surfaces which are actually deflected during various phases of the flight. And so essentially it modifies the aerodynamics of the aircraft because the shape is modified, the airflow over it is modified, and therefore it does a few things which are essential from the point of view of the aircraft's control and stability, and also special situations like takeoff and landing, etc. Right? Now, most of these are trailing edge devices. In other words, whether it's the wing or the horizontal tail or the vertical tail, if you take a cross section along their length, which we call as typically the span, then you see that it's an airfoil cross section. Typically for the wing, the tail, both the vertical as well as horizontal, many a times you use symmetric airfoils, whereas over here you use a cambered airfoil. In other words, there's no symmetry when you join the leading edge and the trailing edge. So those of you who know with a non-aerospace background, this is essentially called as the leading edge because that's the one which phases the flow first, and this is called the trailing edge which phases the flow last. Same is the case with the other aerodynamic surfaces as well. So if you look at most of the aerodynamic surfaces that we are talking about to reconfigure the aerodynamics, you see that they are all essentially at the trailing edge. So many of you will be presenting this on Wednesday, but one of the important things that was understood quite some time back was essentially the kata condition, which essentially is about the flow being smooth at the trailing edge. In other words, there's no turning around the trailing edge, and that has a lot of significance not only in answering the question that was asked, but also in many other aspects of how the flow takes place over the aircraft, and therefore what are the forces which are generated. So keeping that in mind, essentially when you're trying to deflect these trailing edges downwards, for example, in the case of the wing or the horizontal tail, what you're essentially doing is to increase the camber. So, and that in turn modifies the lift characteristics, or how the lift versus angle of attack, essentially that curve looks like, that kind of gets modified, and that is what we typically try to utilize. Okay. So once it is deflected downwards, essentially what you're doing is you're increasing the angle of attack. And as a thumb rule, you should recognize by now that even if you're from a non-aerospace background, that you have a slightly larger angle of attack, then you're going to generate more lift, all other things kept the same, right? So of course, this does not continue forever. There is a particular maximum that is reached, what we call as the stall, a particular angle of attack at which the lift starts going down. Okay, so since we mostly operate at least passenger aircraft, commercial aircraft within the stall or above the stall speed, therefore, or in other words, the angle of attack is below the stalling angle of attack. Therefore, that is not an issue. So most of the time it is CL, or the lift coefficient, which is defined in terms of the lift, which looks like this. Okay, so if so, you define the lift coefficient as the total lift that the aircraft is generating divided by the dynamic pressure times a certain reference area, for which we typically use the planform area of the wing. So in other words, when you're looking from the top, what is the area that is projected by the wing, that is essentially that. So sometimes it's written as S subscript W to refer to the wing area, but since it's mostly understood and we'll use it quite often, we will avoid that particular subscript. Okay, so this is essentially what it is, and this is what is known as the dynamic pressure, that those of you, for example, working on the Bernoulli explanation to the lift will be very familiar with by now, which is essentially 1/2 of the density of air, which is the medium in which the aircraft is flying, of course, at whatever altitude that it is flying at, because it reduces with altitude, as we already saw, times the square of the airspeed. Okay. Again, this is something that we will visit in a more rigorous way as we go forward, because there will be various ways in which the speed is defined. But essentially for now, just take it for now that it's essentially the speed of the aircraft relative to the air that is around it. Okay, so which is essentially going to be different at different locations on the aircraft, but it's kind of in a far field sense, whatever is that angle. So which is why sometimes it's also referred to as V infinity, to show that it is far away from the aircraft, ahead of the aircraft, right? So that is what we typically talk about as the CL, and this CL in turn, for different kinds of airfoils, it varies with respect to angle of attack in a different way, and that variation we typically write as CL versus alpha. And as I said, since most of the time we use a cambered airfoil over here, it may not start at the origin over here. So in other words, it will have some kind of a straight linear behavior for most airfoils. Again, there could be some peculiar airfoils for which this may not be followed. And as I said, once it reaches a certain critical angle, it maximizes that CL, what we call as CL subscript max, and we call this angle as alpha stall, right? So that is what is happening over there. And so if you want to look at this particular line before the stall, since we'll assume that we are not going to be talking about this region, so for most part it is essentially going to be a straight line, which means that we can write an equation for CL in terms of alpha as a CL naught, which is essentially the y-intercept that you have over here, plus an A times alpha, where this A is nothing but the slope of this particular line that you have over there. Okay, and sometimes this is written as CL subscript alpha to refer to that derivative. Okay, many a times we will use these kinds of symbols. In some books, you might even see CL comma alpha, so that it's a derivative of dou CL by dou alpha. So that's how that A is defined. So A is defined as, or CL alpha is defined as, the derivative of CL with respect to alpha. assuming that it could probably change with a few other things as well. For example, Mach number or Reynolds number, etc. So we'll not complicate those things right now. We'll assume that it is flying at fairly low Mach numbers and fairly high Reynolds numbers, so that we don't need to worry so much about the compressibility effects and the viscous effects in whatever we do. So at least in the initial parts, but eventually we will get there and we will talk about those things as well, because it's too much of a simplification when we start saying that the flow is first of all incompressible, because even these commercial passenger aircraft are typically flying at transonic speeds, and locally sometimes they can experience the sonic boom and or higher speeds as well, getting into the supersonic regime. So which means the compressibility effects become very, very significant. Similarly, a lot of books and a lot of simple textbooks would eventually also assume the flow is inviscid, and that is something that some of your teams would have be looking at. I think team right wing is looking at this. Yeah, viscous flow. And so you see the importance or significance of that in their presentation. You will see this Wednesday. So I'll not take the punch out of whatever they say. So let me talk about these things in a little more detail as we go forward in terms of the importance of compressibility and the viscous flow. It's a direct fallout in terms of what this happens. What happens because of this is irrotational flow. Many a times these are assumed hand in hand for a right reason, as you will see in their presentation, as well as what I talk about later on, right? So some of these kinds of assumptions make it simple enough in terms of understanding the equations, but are not really valid as we go to actual aircraft, because it's only when the Reynolds number is actually infinity, or it tends to infinity, this is actually valid, and only when the Mach number tends to 0, this is actually valid, okay? Whereas in reality, you know, these are finite values, and therefore the effects are indeed present, and to what extent they modify, whether you assume these and do, and you relax these assumptions and do, of course, will vary depending upon the aircraft to aircraft and the kind of flight scenario to scenario, but nonetheless, these are going to be very, very important, right? So we have two important results over here. One is the definition of CL. So this is actually a definition, and the symbol that I will be using for definitions throughout the course is to put a, to put a triangle over the equal to sign to refer to a definition. So just like you define the lift coefficient this way, you also define what is known as the drag coefficient, which is the second major aerodynamic force that is almost always generated. So which is essentially very similar to that definition. You just have a D instead of an L on both sides of the equation, and once again you have the same thing with respect to which you are non-dimensionalizing, which is essentially the dynamic pressure in the far field times the reference area, which is once again the planform area of the wing, right? So now these two help us to understand things in a non-dimensional fashion, because if you look at both the numerators, they are essentially forces. So the SI unit for both will be newtons, which is also kilogram meter per second squared, as you know. Whereas in the denominator, you have a dynamic pressure. From the very name, you see that it's a pressure, which means a force per unit area, which is essentially Newton per meter squared in SI units. And this wing area, again in SI units, is meter squared. So essentially, once again, you're talking about newtons at the in the denominator as well in both the cases. So essentially, you're non-dimensionalizing, and CL and CD have no units. Right. So now the idea of going to something like this is that we want to eventually relate these two as well. Okay. And see, because we are generating CL, which is a favorable thing, as you already saw in the last class, the main reason why the flight differs from the surface transport on the Earth is a third dimensional motion. And for that third dimensional motion to be possible, you need a third dimensional force, which is essentially perpendicular to the velocity, and that's essentially lift. But because we are introducing the lift, whatever drag was already there gets increased, and that's what we call as the induced drag. Okay, because we want something, there's nothing like a free lunch. You have to pay for it, and that payment is coming through what is known as an induced drag. So in other words, D involves two parts to it. One which will be there even when there is no lift which is being generated, what we call as the parasite drag, right? So D is made out of two parts. One we call as the parasite drag, sometimes referred to as D naught or DP if you want to call it parasite drag. And then you have also an so-called induced drag that is over there. Okay. And since the non-dimensionalization for both CL and CD is done with respect to the same quantity QS in the denominator, whatever we talk about in terms of L and D will be valid for CD as well. So in other words, the same equation becomes valid when I put a C and make the D's as subscripts, right? So in other words, your CD is composed of two parts. One is a CD naught, the other is a CDI. And this first term, which we said is lift independent. So in other words, irrespective of whether I'm generating lift or not, or how much lift I'm generating from the aircraft, it will always be present. And that CD naught in turn is made out of what is known as a pressure drag and a skin friction drag. Okay, so even when you make this assumption, for example, inviscid, the pressure drag will still remain there. Okay, so essentially like for example, a bluff body, let's say cylinder being in flight. So when there's a flow across it along the diameter, so essentially you're having a certain drag because the conditions of the pressure ahead of the, so for example, let's say this cylinder, and there's a flow taking place over this, then you see that the pressure in the front and the pressure in the back are different from each other. You will have a higher pressure in the front and a lower pressure at the back because of the way the flow takes place. Again, a lot of these things will probably be explained in your Wednesday presentations, so I do not want to go into the details of that. If there is something missing, then I'll come back and try to address those. But that difference in pressure is going to cause this to be pushed backwards. So that's essentially a drag, what we call as the pressure drag. So that's one part of CD naught. The other part is when we relax this assumption of inviscid and make it a viscous flow. On the skin, when there is a flow that is taking place, there is a boundary layer which is happening on top of the airfoil, and there is therefore a frictional force. So in other words, in addition to pressure, which is essentially a normal stress, you have a shear stress which is coming as well, which is acting on a surface, not in the direction of the normal to that surface, but in a perpendicular direction to that normal, which essentially means it's parallel to the surface. And when it's parallel to the surface, essentially shear, and a part of that shear can cause rotations, and that is what has huge significance as well. So CD naught, remember, has these two main parts, even when you're talking of incompressible flow. And then when you bring in compressibility into picture, as you go closer and closer to Mach 1, then essentially you're having a wave drag as well, which is coming in. But while all that is happening, this CDI that is essentially there, that portion alone is given by, whereas here we had a linear curve, here we are going to have a quadratic behavior. In other words, a constant K times CL squared. Right? For simple situations where you have, let's say, an elliptical lift distribution along the wing. So in other words, the lift is not a constant along the span of the wing, right? It reaches a maximum close to where the wing is attached to the fuselage, and then it slowly drops down to zero at the ends, okay? So when you have an elliptic lift distribution like that, this K is given by 1 by pi times what we call as the Very good. Yeah. Aspect ratio times E, which is known as the Oswald efficiency. That's okay. Thanks. So you have your CDI equal to CL squared divided by pi times aspect ratio E, typically about 0.7 to 0.8 depending on various factors. We'll take that up when we look at the various complications in the definition of the shape of the wing and the overall fuselage as well. Okay, and this is something that is again a very important design feature of aircraft, which is essentially if you have this tip to tip distance of the wing, we call as the span, and we usually use the symbol B to refer to that. Many times we'll be talking of a semi-span as well, which is B by 2. And at the end of last class, somebody was asking me about the lift that is generated where the fuselage actually is coming in and therefore the wing is getting into it. Again, the way the wing is attached to the fuselage will be different in different situations. Here you see pretty much what is called as a low wing because it's towards the bottom of the fuselage. You could have a mid wing where it's attached to the middle of the fuselage, or the top wing or a high wing, which is essentially when it's attached right at the top, right? Each of them have advantages and disadvantages under different situations, and we'll talk about those things a little later. But right now, what happens is, of course, since that is not seeing the flow, in other words, it's blind to the flow, therefore, obviously, that portion of the wing is not going to generate any lift. So you'll essentially have a wing box, and typically there's also what is known as a keel beam at the bottom of the fuselage, which is going to help make this structure strong enough because a huge amount of force is coming from the wing, which is the lift and the drag and also the moments, which we'll talk about a little later, especially the pitching moment over here. And all of that is getting transferred from the wing to the fuselage, and that needs to be resisted, which is why you see a much larger cross section over here. One of the reasons why you see a much larger cross section over here. The other, I think I mentioned in passing in one of the previous classes, because as you go over there, the high pressure and the low pressure at the bottom and the top respectively is going to get balanced out because of vortices which are generated at the end, which are tip vortices, and therefore you will see from the explanation of at least one of the teams that there's no lift which is generated over there, or approximately it is zero, negligible compared to the lift which is generated there. So which is why, of course, as we said, in terms of the lift distribution, it is kind of parabolic when we say over here and over here. So essentially this is the lift which is being generated along the length of the span, which has to be integrated over the length in order to get the total lift which is generated by the wing. Of course, there will be some lift which will be generated by the horizontal tail as well. It could be positive or negative, so they have to be algebraically added up. The contributions of the fuselage and the vertical tail will be negligible, but to be accurate enough, we need to kind of combine all of these things in place. So it's only when you have an elliptic lift distribution like this that this particular thing is valid by AR as such. Once you have a non-elliptic lift, you will have this Oswald efficiency kicking in and therefore reducing it even further, and which is one way in which the efficiency, which is of course less than 1, and therefore you see that the drag is higher when you're compared to when the efficiency was 1, which is essentially for the elliptic lift distribution. So now you have this particular situation that is there, which is coming to your CDI. We already talked about a CD naught. So now you see if you draw this total CD that is there, which is CD naught plus this, where CD naught is a constant with respect to CL, then you see that if you plot versus CL, the CD, then it's going to have something like this, which is quadratic curve that is over there. Okay. The reason why this is not at the center is because you have a constant term that is coming, which is kind of pushing it, and therefore you would have something like this, right? Oh, I'm sorry. This is, yeah. So this should be over here. Okay, so this is KCL squared. So therefore, it's very clear that for CL equal to 0, it is minimum, which is essentially the entire pressure drag and skin friction drag put together. And that's what we call as the drag polar. So this quadratic equation plot of CD versus CL, we call it as the drag polar. Since CL is something which is desirable and that is what you're trying to generate, you cannot avoid it. So therefore you cannot avoid the induced drag also, therefore the addition to the parasite drag that is there. Then we will see once we get to some optimization problems, how these can be kind of correlated for certain optimal performances. Either you want to, let's say, maximize your L by D, which is the lift to drag ratio, or the thrust to weight ratio, which in cruise are kind of correlated with each other. But in other phases, there can be other variables which are kind of influencing this as well. So these are some of the terms that we will be talking about quite frequently as we go forward, and therefore it's very important for all of you to get familiarized with that. Now, coming to the wing itself, as we said, when you take a cross section, whether you take of the wing or the horizontal tail, or for that matter the vertical tail, you're going to have a airfoil cross section, right? Now, this airfoil cross section is what we refer to at the front portion as the leading edge, and the rear portion over here as the trailing edge. And here's where you will have what is known as the kata condition that I mentioned earlier, and you will see more of it being talked about in Wednesday's presentation, after which I will continue talking about it. But this is introduced just to show that there's a line joining the leading edge and the trailing edge, the length of which we typically call as the chord. And for subsonic and transonic flights that we'll predominantly be dealing with, the resultant effect of all of the aerodynamic forces that are being generated, if we call that force as, let's say, let me just... If I call this force as, let's say, A, that's the total aerodynamic force that is being generated, you will have, if you have the velocity in this particular direction, which is your V infinity, then you will see that perpendicular to that, you'll have what is known as the lift, which we were talking about earlier, and parallel to that, you will have the drag. So your A is a resultant of that L and D, and then you will also have a moment that is coming about here, which we call as the pitching moment M. And this particular point, purposely I've drawn it such a way that it's about a quarter of the length of the chord. So which is what is known as the aerodynamic center. Now this is for subsonic flow. Again, what we're talking about, almost incompressible, or compressibility effects are very small. As that becomes more and more and you enter supersonic or hypersonic regimes, that gets pushed back to about half the chord, right? But we will mostly be focusing on this particular location. There's an advantage. See, whenever you have a pressure distribution and when you have viscous flow, you'll have a shear distribution. The net resultant of that is what is this particular force A, right? And depending upon where A acts, your M can actually become 0 or positive or negative, right? So you have a choice over how that thing can actually be put, where the resultant can be put, by modifying the moment that is generated because of that resultant force, or the stress distribution, which is essentially the pressure and the shear which is acting on the surface over here. Now, when you're talking about that particular location, there's a certain advantage, and when we mathematically derive, we will show there is what that particular advantage is in putting at the quarter chord in terms of the simpler behavior of the pitching moment and the various forces that are generated, in particular the lift and the drag. Now, let's keep that aside. Now, when we want to get into, are there any questions or doubts so far on this, especially from non-aerospace background people? Because this class is especially for you to get familiarized with some of the terms that those with an aerospace background are already very familiar with, so that you then come to at least a closer to a level playing field. So any of you have any questions or doubts on this, whatever I've spoken, please. Yeah.
So regarding aerodynamic center, will it be like center of pressure, whatever we say, will it be same?
Very good question. Very good question. So essentially what I'm talking about here is what is called as a 2D flow, because I'm showing only the cross section, which means that I'm talking of an infinitely long wing. Okay. So in other words, we introduce this concept of aspect ratio, which is essentially, I think I didn't define that. So I started with that, but I forgot. So your span B divided by the average chord C bar. That is, you see that the chord is very large over here, the length of the line joining the leading edge to the trailing edge, and then it becomes very small over here, what we call as a taper in the chord. Similarly, there will be a taper in the thickness as well, right? So for many reasons, few of which, major ones which I mentioned, essentially the structural behavior and also in terms of the aerodynamic behavior of this. Now, these are 3D effects. The fact that there is an elliptic lift distribution over there is essentially coming because you have a finite sized wing. In other words, you don't have infinite aspect ratio, and therefore you do not have a 2D flow luxury that you have over here. So what was your question? Yeah, so here what we call as the center of pressure essentially becomes your aerodynamic center over here when you're going to the 3D flow, because there are certain other aspects of the 3D that we are going to bring into picture. But when you're talking about this particular thing, we are essentially talking of that, and especially for inviscid flow, when pressure is all that is acting, and therefore you do not have any shear stresses which are coming from the viscous flow. I'll come to you. So once you have that situation, then essentially it's the resultant of all of that pressure, where that force is acting because of that, that is your center of pressure. But your aerodynamic center is defined in a more convenient way, because you're generating this pitching moment as well, and then you want to see how it changes with alpha, for example, and then based on certain aspects of simplifying that, which I will explain more clearly when we go to the equation, you define that particular aerodynamic center in that particular way. Yes, please.
So you said aerodynamic center and center of pressure are same in airfoil.
Yeah.
But center of pressure will change the angle of attack, but aerodynamic center it will not change. It will be at the quarter chord.
That's correct. So there are certain things, again, it's going to be all dependent upon the viscous inviscid flow, etc. So those things are also going to come into picture. So we will define that in a little more generalized fashion later on. Okay. So there are more differences than what I already mentioned. Yeah. Anybody else? Any other questions? Okay. So with that, I think one more thing that we would like to see is, as I said, all of these or almost all of these surfaces that we have shown in color over here are essentially in the trailing edge, but the exceptions are what we call as the spoilers over here, which increase the drag purposely when they're deflected, which is, for example, very useful. For example, when you're landing, you want to reduce the speed much faster than what it actually would do otherwise. And then you have what are known as the leading edge slats, which essentially again droop down and therefore create a gap between where they are attached to the wing, and therefore let some of the high pressure air flow from the bottom, which is bottom of the wing, to come up to the top surface, and therefore it will do what is known as a delay of the flow separation, and therefore maintain the flow to be laminar for a larger length along the chord, and the turbulence will set in either later or can be completely avoided in certain situations. So what is the advantage of that? Again, there are lots of things that you guys are going to be talking about on Wednesday, so I don't want to again take the punch out of you. So you will talk about those aspects, maybe not in terms of the slat itself, but in terms of what energizing the air flow on the top surface can actually do in terms of the lift that is being generated, right? First of all, the pressure distribution, and therefore the lift that is being generated. Now, so these are all the aerodynamic surfaces that are used, and we already talked about some of these when we were talking about in the previous class, referring to the various control surfaces that are over there. So one is when you are trying to roll, you are having what is known as the aileron deflection. So if you want to roll with your starboard, which is your right wing, going up, you want to increase the lift on this wing, and you want to decrease the lift on the left wing or the port wing, right? So when you want to increase the lift, you always deflect the control surfaces downwards. And now, because the purpose is to generate not just the lift difference, but actually a moment. One way, of course, is to increase the force. The other is to increase the moment arm. That is how far that change is happening. So which is why you will see that the surfaces in red, marked in red over here, are essentially your ailerons. So when it is deflected down, this, in other words, the right or the starboard wings aileron is deflected down, it generates an extra additional lift, which is going to make the aircraft roll to the left, right? So again, we'll come to the axis and the positive and negative nature in the next slide. So right now you see that this is what is actually happening, right? Now that's not only because what's happening on the starboard wing, but also on your port wing, because you see that it is differentially deflected here, because here it's deflected downwards, the red portion. Here the red portion is deflected upwards. When it is deflected upwards, you're essentially reducing the effective angle of attack over there, and what that is going to do is to reduce the lift, like what we saw in the CL versus alpha curve, and therefore that is going to have a lesser lift than what it was already generating. So the net effect of both of these is what is going to help. Now, of course, you could have had that inboard, but then what would be the disadvantage is that the moment arm is going to be much lesser, which is why you have them outboard. Whereas in the portion which is closer to the fuselage, you have these purple colored lifting surfaces at the trailing edge, which are called as flaps, and the reason why you see them all going in the same direction is essentially to increase the lift that is generated. And you will typically see, if you have a window seat on your aircraft, you would see that during takeoff and landing, that is usually deflected so that you increase the lift in landing, because you want to have a smoother landing so that it doesn't drop with a thud because of the weight, right? So then you have these kinds of surfaces, and of course, as we mentioned, the speed is also reduced in landing by deflecting the spoilers. Then coming to the green surface over here, typically operated with the rudder pedals of the pilot, whereas this particular thing is by the stick moving to the left and the right. The ailerons are moved. Here it's by pressing the left and right pedals, the pilot will be deflecting the rudder in different ways. So now if the rudder is deflected, for example, towards the right, that is towards the starboard wing or the starboard tail, then essentially what you're doing is that very similar to what you're looking over here. You're having a lift which is going to be in this particular direction. In other words, there's going to be a yaw to the right. Okay, so in other words, you have deflected the rudder to the right and you're getting rotation towards the right. Similarly, the opposite direction, the left direction. But as I have cautioned you quite a few times earlier, just like in your motorbike, you know that when you want to take a sharp turn, you will have to bank. So in other words, you will not just turn like this, in other words, you will not just yaw like this, but you will actually roll as well. So that roll is what we talked about over there, how to generate that roll. So typically the rudder pedals and the pilot's control stick in terms of left-right motion will both be done simultaneously. So, and only when you see both of them done simultaneously, you can have smooth coupling between them. And once we have the equations for the coupled motion of the roll and the yaw, along with, of course, the side drift, then we will see why I'm telling what I'm telling right now. So right now, without the math that is involved in explaining the physics, we are just trying to understand it from a physical perspective as to what actually happens. Yeah.
Sir, you mean to say we cannot give rudder command without any aileron command?
No, it depends on what exactly you're trying to achieve. But if it's essentially to change the heading of what you're doing in a smooth fashion, then you typically do it. There will be a lot of maneuvers and other situations where you might operate these in a separate way. Would that be right?
I was just thinking tailless aircraft.
Yeah?
Tailless aircraft.
Tailless, yeah.
Just
Right.
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 So,
Yeah.
as he has already brought out, it is a combination of lot of things that happens. It's not just one.
Right. So here we are trying to build up the thing to understand some of the major effects that are there and try to see which cannot be done in an independent way, because the coupling is very strong. There could be others which are kind of coupled in a weaker fashion also, and many other things will be generated, right? So that is as far as the rudder is concerned. The next thing is when the pilot moves the control stick forward and backward, or the control wheel, depending on the kind of aircraft, then what you do is you are deflecting these light blue colored surfaces that you see over here, which are called as the elevators. And what he referred to is when you have the wing and the horizontal tail combined, you have what are known as ailerons, where the elevator and the ailerons are combined. So right now, let's keep things separate so that we understand the three different kinds of rotations that are happening over there, right? Though coupled. Now, coming to the elevator, it is much simpler because it's not coupled like the roll and the yaw. It's an independent thing that is being done over there. And once you deflect it downward, you see that the lift which is being generated by the horizontal tail will become larger. So in other words, it's possible, depending upon the incidence angle of the tail, the way the aircraft is designed, it might be such that the tail might actually be put at a lower incidence angle, so that it's actually generating a negative lift. So in that case, when you're deflecting the elevator, you'll reduce the value of the negative lift and move closer to zero, and maybe even towards the positive, depending upon how effective the elevator is and how effective you want the elevator to be as a designer, right? So once you have the way it is shown in this particular picture, which is essentially deflecting the elevator downwards, you see that there is a force which is generated upwards, or the downward force is reduced. So essentially, it's an effective upward force, and that about the CG of the aircraft is going to cause a rotation like this, what we call as the pitch. Now, that pitch, nose up is considered positive, nose down is considered negative. And for all the others also, we use what is known as the right-hand thumb rule. So once we introduce the coordinate system, which we'll do in the next slide, it will become clearer. Depending upon the positive directions of the axis that we introduce, a right-hand thumb rule will give you the corresponding positive rotations that are involved. So I think I've covered everything on this particular slide. So let me move on to the next one. Okay. Now, you see that here you have the axis being introduced, and this is very important because we are actually going to be introducing 4 sets of axes. This is the first set that is attached to the body. So in other words, and this point O is the center of gravity. Remember that I said when we were talking about the syllabus, there are 6 degree of freedom model for the rigid body and a 3 degree of freedom for the rigid body, which means that the rigid body is going to be shrunk to a point. So in other words, all these rotations that I'll be talking about will all be in a much more simplified sense, and to a certain extent it's even crude, but it's important for us to start simple and then start making things a little more complicated based on the necessity rather than just for the heck of being complicated, right? So essentially you have this CG, and we're talking of a 3 degree of freedom system, and you have a point mass. You do not have any of these rotations that we already talked about. So essentially you're talking about just 3 spatial coordinates in order to fix it, right? Anywhere compared to some other reference frame that you have. Now, therefore, it's very essential to bring in that some other reference frame, which is what will eventually lead to a set of 4 reference frames at least that we will be dealing with over here. So now the first set of reference frame has all its axes having its origin at the CG, as I already mentioned, and we are denoting that location of the CG by O. In general, you will see that there can be a shift in the CG also, and in fact we will be talking about it quite a bit because it has some implications towards the stability and control when we get over there. But right now we are assuming that for the small phase of flight that we are going to be talking about, where the equilibrium is concerned and therefore the equations of motion are derived, we'll say that the CG is at a fixed point that you have. One of the reasons why the CG would change is, of course, the fuel burn that is happening, and a fairly large weight fraction of the aircraft is the fuel, and as you burn the fuel, it's going to change. Of course, symmetry is ensured. In other words, if you look at this sketch, the XB, which is going towards the nose from the CG, and ZB, which is going downwards from an aircraft perspective, XB, O, ZB form a plane of symmetry. In other words, the right to that is the starboard portion and the left to that is the port portion, and you maintain that symmetry. So even when fuel is burnt and you have, let's say, fuel tanks in both the wings, then it's ensured from the design perspective that as you burn the fuel, equal amounts of fuel are burned from the left and the right in order to make sure that that particular symmetry is maintained in as many respects as is feasible, right? So, of course, there will be certain negligible effects, like, for example, in a passenger aircraft, how the seating is done and how many people are sitting on the left portion, the right portion, and things like that. To some extent, the seating algorithms in the airlines also try to ensure that, but these are much smaller weights compared to the overall weight of the aircraft, and therefore will not make too much of a difference in terms of that symmetry. Overall, that particular symmetry of the XB-O ZB plane is kind of maintained, and that's what results in, even when you go to the 6th degree of freedom problem and have 6 equations of motion governing, as I said earlier, we will have a split that is going to happen between the 6 equations, 3 which are going to be coupled with each other, another 3 which are going to be coupled with themselves, but these 2 are decoupled from each other. These 2 sets are decoupled from each other, and that is essentially one of the set is essentially motion within the plane. If it's motion within the plane, then you are essentially talking about forward motion. You're talking of the vertical motion that is happening, and you're also talking about the rotation which is happening there, which is what we refer to as the pitching motion because of the elevator deflection that is over there, because that is also happening in the plane of symmetry of the aircraft, whereas the others are going to spoil this particular symmetry, whether it is yaw or whether it is roll. From whatever initial plane you had, it's going to change that, or a drift for that matter, in the direction what we are referring to as YB over here. Okay, so these are the body fixed coordinates that you have over here, all coming from the CG, and the roll, pitch, and yaw are essentially defined with respect to them. So in other words, when there is a rotation which is taking place about the positive xb axis, the positive xb direction is going from the CG towards the nose of the aircraft. The one which is going downwards is your positive ZB direction, and the one which is going towards the starboard or the right wing is essentially your positive YB. So based on that, you see that you use the right hand thumb rule to explain the positive roll direction. So this is essentially the roll that is happening over here, which is the roll where the right wing is going down and the left wing is going up. So essentially this is a positive roll that we are talking about. Similarly, that is about the XB axis. Now coming to the YB axis, that is where the pitch is there. Already mentioned that the nose up pitch is considered positive, and that you can see from the explanation from the coordinate perspective or the right hand thumb rule also, because the y-axis is positive, or YB axis in particular is positive along the starboard or right direction, which means when you use the right hand thumb rule, this moment or this rotation is essentially positive, which is nose up, right? So that is the second. And finally, the yaw direction. So now it's going downwards, and therefore the rotation has to be like this. So once again, a rotation towards the right or a yaw towards the right is considered to be positive. Now, as I said, the name of the course is Flight and Space Mechanics. And when we talked about mechanics, so in the previous class, we said that, or dynamics for that matter, you're essentially talking about two parts to it. One is where you'll be talking about the kinematics, and the other is dynamics, where sometimes it's also referred to as the kinetics. So already defined to you that this is something where you're only describing the motion. So in other words, you're not talking about the cause of the motion. And the cause of the motion, essentially, when you're trying to change an existing state, whether it's at rest or of uniform motion, then obviously you need to apply a force, or in a more generalized sense, force or a moment. So that is what is going to generate that particular motion. But even before understanding that cause, which is what is dealt with in the kinetics, you're trying to deal with just the description of the motion. And just while I was trying to describe this to a dynamics class, undergraduate program of the Georgia Tech a couple of summers back, it just happened to, while I was writing this, just happened to notice purely from perspective of the spelling, what is the difference between these two words is essentially your MA. And if you remember what is going to be the cause of that particular motion, it's essentially your force. And that force in your force is essentially your MA. And this is, of course, a vector equation which is over there. So when you're actually talking about the description of the motion alone, you're actually talking about without that force, which is actually kind of inbuilt into that whole thing. It's purely, we are not just that, we are not taking into account in the equations that are being used, but at the same time, that motion would not be possible without a cause, and that cause is what we go to next as in terms of the kinetics. So whatever the aerodynamic force A and its resultants L, D, M, etc. that we talked about in the previous slide, all happening in the plane of symmetry, XB, O, ZB over here. All that is a topic which has to be covered in the kinetics. But even before we go there, we have to talk about the kinematics, which is essentially the positions and the velocities, how they are related to each other. So in some sense, by introducing a coordinate system and the CG and talking about a 3 degree of freedom system, we know that we are going to follow the motion of this particular point O without talking about the causes of that particular motion, right? Now, when you are talking about that particular point O that is over there, you have to have a reference with respect to which that you're talking about its motion, whether it's the location or the speeds in the different directions. And when you're doing that, we will keep in mind that we are not going to stop with kinematics, but we have to go to kinetics, where we will introduce this particular relationship and its generalized version, which is essentially the moment vector, which is going to be given by the inertia tensor times the angular acceleration, right? Times the angular acceleration that you have over here, right? So, okay, truly speaking, this is a second order tensor, but we have to put two underlines instead of one that we do for vectors, but we will not complicate this course with things about that. So we'll just use matrix analysis because it's already described with respect to a particular coordinate system. So the tensor will become a square matrix that we'll be dealing with, that is the inertia matrix. So these two is what will take us from the kinematics to the kinetics. But these two are valid only under certain situations. This is what we call as, of course, Newton's second law, as you're familiar with. While this is what is known as Euler's law. Of course, Euler has worked on many different things. So many things will be named after him. But this is one thing which is named in rigid body dynamics after him, is just an extension of Newton's second law to rotations, and therefore rotational accelerations and moments which are going to be generating that in terms of the moment of inertias that are involved and products of inertia that are involved for the body in question, right? Now, those decouplings that we talk about will happen in both these equations, which is why we will have two sets of coupled equations, both having three equations each. Okay. Now, for either of these to be valid, first of all, this, because Euler essentially derived it from that. So, if you're talking about the validity of this, there are under certain conditions only under which this particular is valid. So, what are some of those major conditions? Anybody recollect? When is F equal to ma valid? Point mass, okay. Yeah, because we are not dealing with moments. So point mass, very good, which is what we are going to apply it to for the CG. So it is relevant application in our case. Anything else? Yeah, M constant, very good. Yeah. So because otherwise the more general version of this would be the rate of change of the momentum, right? So that is essentially M times V. So which will involve an M dot times V plus M times V dot. Okay. So which is something that, of course, all these V's. Okay, all these vectors we have to be very careful with, because whenever you're talking about a derivative of a vector, even with respect to a scalar, we have to mention in which frame we are taking that derivative. Okay, so that is very critical. So what you're telling is absolutely right, that we are essentially assuming that this is approximately 0. Otherwise, this is not valid. So this rate of change of translational momentum is what the actual more generalized definition of Newton's second law is. And similarly here also you can talk about an I times omega and the whole thing time derivative. Then you are talking about the M, so that I changing with respect to time can also be accounted for, just like here M changing with time. Okay, so it's not so difficult if you have a change in M, because in most cases, especially in aerospace, you'll have a huge amount of fuel burn that is there, which means the weight of the aircraft will come down by quite an amount, and therefore the M dot makes a huge significance. And it will become even more important when you're talking about rocket propulsion for spacecrafts, where both oxidizer and fuel or propellant are burnt together as a propellant, which means that you are reducing the weight at a much faster rate than you would in the case of an aircraft, because the fractions of weight for the propellant is much larger typically for most rockets compared to the fuel fraction, weight fraction for an aircraft. Okay, again, it depends upon the specific application of the aircraft, etc. It can have a wide range, but still overall you will see much lesser values. So this becomes a very important term when we go to rocket propulsion. So anything else? When is even this particular equation valid? One thing what you said is correct. It's for point masses or particles. Anything else? Yeah, frame of reference. Very good. So that's one of the most critical things that you should remember. That is, this is valid, both this as well as that are valid only for okay. So what do you understand by a frame of reference being inertial or not? Very good. Yeah. So very direct, straightforward definition of that is when you do not have the frame itself accelerating, then you have an when frame itself is not accelerating, then you have an inertial frame, and when the frame is accelerating, you have a non-inertial frame, right? Now, when you talk of acceleration, remember that the definition of acceleration is the time rate of change of the velocity. Okay. So, and as I said, whenever you're taking the derivative of a vector, when velocity is a vector, you have to mention in which frame of reference you're taking that derivative. So let's say there is a frame called I, which is an inertial frame of reference. Then you're taking with respect to that. Because if you're taking with respect to any other frame, you will get different expressions for the acceleration in this case, but whatever derivative of whatever quantity it is in any other case. So always remember that when you have a scalar whose derivative you're taking, you do not need to mention the reference frame with respect to which you're taking the derivative, but whenever it's a vector or tensor of higher orders like a dyadic, etc., in all those cases you do need to mention this. You will not encounter most dyadics, etc., but vector, which is a first order tensor, we will keep encountering very frequently, be it force or velocity, acceleration, position vector, etc. Whenever you're taking that derivative, always remember to put this superscript ahead of the d, which essentially means that it has to be taken with respect to that frame of reference. Very easy to see why it would be different. For example, if you take it in with respect to any other frame, you would have to express this v in order for it to be calculated. There are many ways of doing it, but for example, if I want to calculate this d by dt in I would put v in terms of unit vectors in that system I. Let's say I call it ijk. Then with respect to that particular system, ijk will not vary with respect to time. It's only the magnitudes of those, each one of those components, which will vary with respect to time, and therefore I need to take only the derivatives of the coefficients of ijk, not of ijk itself. But on the other hand, if I'm taking the derivative with respect to a different frame, let's say the B frame, then I have to rewrite v in terms of the unit vectors that I introduce along this. So suppose I introduce the unit vector along x direction, which is tangential to the x-axis, as IB, along the y direction as JB, and along the z direction as small k b. So when I introduce that, and I want to take, let us say, a derivative with respect to the B frame, then I will have to express the V in terms of the coefficients of IB, JB, and KB. And you know that in general, they may not be the same as what they were with respect to IJK, which were the unit vectors for the I system. So and therefore the time derivatives of that will also be different. Okay. It's not that you have to every time express this in that particular frame of reference in order to calculate the derivative, because you might also know how to calculate the time derivative of unit vectors. If you know what is known as the angular velocity of a frame of reference or a rigid body, you can use that as a cross product, because the d by dt of unit vectors, or for that matter any vector, is also equivalent to taking a cross product with omega, the angular velocity. Anyway, we will visit that when we get to that, but right now let's not complicate. Even from a simple manner, you know that in order to take this derivative, this involves both magnitude and a direction, and this change with respect to time can happen either because of the change in magnitude of v, or because of the change in direction of v, or because of both. Okay, so keep that in mind. Very similar to what we did here, the product rule. When we had m and v, we say keep m constant and take the derivative of v. Keep v constant, take the derivative of m, right? So that's what we were trying to do over there, right? So in other words, similarly here, you're talking about a product, which is a product of the magnitudes along each one of those unit vectors times the corresponding unit vector. And either one of them can change with respect to time, or both can change with respect to time. You should be very clear about that, which is why this superscript is very, very important. So when you're talking about these things, even in presentations or in your individual reports or even in the final exam, I want to you to ensure that whenever you're dealing with any derivative with respect to any scalar of a vector, then you ensure that you're putting the correct frame of reference with respect to which you're taking it. Now, we will interchange these quite a bit, and it is a valid interchange that instead of talking about a frame of reference, I can talk about a rigid body, because all rigid bodies can typically be used as a frame of reference, and therefore we can interchangeably use these two words. But essentially you're saying that you're describing the position or motion with respect to a particular body or a frame. And when we're talking about these inertial frames of reference, as he pointed out very correctly, it's non-accelerating. And when it's non-accelerating, you know that A is given by this. So essentially you're saying that neither the magnitude nor the direction of the velocity should change. In many cases, you might have the magnitude remaining constant of the velocity, but the direction is changing. Very simple is a rotation, which is like an orbital rotation that you're talking about, or just an aircraft taking a curve, right? So in both those situations, the magnitude of the velocity might remain the same, but its direction is changing, which means that there is a non-zero acceleration that is happening, and that means it's a non-inertial frame of reference, and therefore this is not valid. Newton's second law, or what is derived from that, the Euler's equation, neither of them are valid in such a situation. So it's incumbent on us to determine an inertial frame of reference before we move from kinematics to kinetics, because we will be involving forces and we will be relating whatever motion description we have given in terms of positions, velocities, accelerations, etc. We will be relating that to the forces and the moments, and therefore that can be possible only if and only if we are referring everything back to at least one inertial frame of reference. So very clearly, we have introduced only one frame of reference so far, which is the body fixed frame of reference, having its coordinate axis as xb, yb, zb, and its unit vector system as ib, jb, kb. Now, this is an accelerating frame of reference, because that point mass can change its velocity, and it can also not necessarily travel on a straight line, but can travel on a curve. Even if the speed remains the same, the direction is changing, and therefore there is an acceleration. So xb, yb, zb system cannot be an inertial frame of reference. So we need an inertial frame of reference. So what do you think could be a right candidate for that? Okay, so let's bring the Earth into picture over here. Of course, the problem with the scales that we see over here. because at the size of an aircraft, actually the Earth is, and also the altitude at which it is flying, let's say 10.5, 12 kilometers, the Earth is pretty much like a flat surface, okay? So, but now if you're talking about the Earth, and with respect to that, let's say the CG of the Earth is over here. Let's call that as E. And with respect to that, we will now introduce, again, just like we introduce IB, JB, KB unit vectors and the coordinates XB, YB, ZB, we'll just replace the B's with E and use a consistent convention in naming these quantities, right? So now you will have, let's say, an Earth fixed frame of reference. You will have, let's say, an XB, a YB, XE, and a ZE, and corresponding to that, again, you'll have unit vectors, IE, so vectors we can refer to either by putting an arrow on top or an underline as we did over there. There are two equivalent ways of doing it, especially when you're writing either on a board or in your presentations or in your exam. But in many books, you would see that instead of either the vector on the top or the underline, you would have a bold character. So you'd have a bold character for all vectors, whether it's unit vector or the other kinds of vectors like velocity, acceleration, etc., that you will be familiar with from many other courses that you have taken, right? Now you have a set of axes over there. So do all of you buy that argument from him that you can't treat this XE, YE, Z system as an inertial frame of reference?
It is also an approximation. I mean,
Yeah, it's good to say it yourself, right? So essentially, what is the approximation that is there?
we are ignoring that the entire Earth is also moving around the sun.
Correct.
So that we are saying that acceleration can be ignored for the practical purposes.
Very good. Yeah. Right. So one of the counter arguments there for what he said is what he himself has said again, that essentially the frame of reference we want is inertial, which means it should be non-accelerating. And if it's non-accelerating, we already saw the motion should be in a straight line and it should be a constant speed, right? Now, if you see the Earth, it's actually rotating, right? And it is also revolving, as he mentioned, around the sun. And that is actually a curved path. It's not a straight line, right? So it's a curved path in which it is revolving and it is rotating. And to add to all of these, the axis of rotation of the Earth is not always maintained the same. In other words, the axis of rotation has a very small precession that you have that is also going to be complicating the overall idea of Earth being a inertial frame of reference. So there are people who go beyond the Earth, let's say fix it to the sun, right? So that is one option you have instead of the Earth, which is rotating and revolving around the sun. You fix the inertial frame of reference to the sun. Is there something wrong with that as well? Yeah, exactly. So the solar system is also moving around in the Milky Way galaxy. Then if you fix it to some other star, then again the galaxy itself is moving. Then something to the center of the universe or whatever, you see that the universe, again, you don't know where exactly the center is. There's a lot of debate on that. And again, it's an expanding universe. And so there's no end to it. From a scientific perspective, Newton's laws can never be applied because there's no such thing as an inertial frame of reference. So what we are doing is taking a step back and saying, no, we're not scientists, we are engineers. And so we'll take what works to a reasonable extent. There will be errors, but if we can live with those errors, because those errors are very small, then it's good enough. So that's exactly what happens when you take the Earth as a frame of reference. So what he said is right, that it is a reasonable assumption to an inertial frame of reference, though we know it's fairly fast spin from a velocity point of view. It might look that it's taking one full day to make a rotation, but remember that it is 6,400 kilometers and the circumference is about 40,000 kilometers. So it's covering 40,000 kilometers in 24 hours. So that's a fairly high speed at which it is rotating. Precession might be fairly small, slow speed, relatively speaking. And also this is happening over a year, but the distance involved in terms of going around the sun, the revolution, is also fairly high speed. So now, and also it's curved because it's an elliptic path that you're having. So truly speaking, there have to be corrections for all of these non-inertial nature of the frame of reference with respect to which we are taking it, but we take it with a pinch of salt. We are aware of that, but we are willing to live with that very small error that is going to happen because of that, right? So that is essentially what we are going to be talking about. So that's why we introduce this, and we will take all these derivatives when especially we want to apply either F equal to ma, or we want to apply m is equal to I alpha, or the full forms of that, which is the d by dt of mv or d by dt of I omega. Then we want to apply those. In all those four cases, we need a frame of reference which is inertial, which is non-accelerating, which means constant speed and no rotations or revolutions. But in spite of this having rotations, revolutions, not a constant speed, you will continue to use that as an inertial frame of reference. Okay, so that's as far as this is concerned. Any questions or doubts about this? So far, we have introduced two sets of references. One is the B system, which is fixed to the body, or in other words, the aircraft, and it's therefore having an origin at O. Then the second one is at the center of mass of the Earth, and it's having subscripts E referring to the Earth. Now, the third system will be very simple. Instead of rotating this system, you keep this system as it is and take it to O. In other words, just a translation of this frame over here. And typically, nothing much changes when you're translating a frame of reference. Okay, so most things that are valid with respect to that continue to be valid with respect to this, as long as this is maintaining its orientation with respect to E. Okay, we will call that as the H system, referring to horizon. So in other words, the axis will be parallel to XE here, which we will call as XH. Similarly, axis will be parallel to YE, which we will call as YH, and an axis which is parallel to ZE, which we will call as ZH. And correspondingly, IK, IH, JH and KH are the unit vectors along these three directions, which will be exactly equal to IE, JE and KE respectively, right? So, but the body is moving when we say, and most of the forces that we are calculating, we're all with respect to the velocity. So in other words, the relative velocity of the aircraft with respect to the medium around it, which is the air, is what is important for us. It's not the velocity of O with respect to E that is important for us. Yes, this position vector that you draw from E to O, so this position vector, which I call as R or P, from E to O, if I take the time derivative of that, I will get the velocity with respect to this frame of reference. In other words, the velocity of the CG of the aircraft, right? But then if I want to calculate all the forces like lift, drag or pitching moment, etc., this velocity will not be of any direct significance for me. I need the velocity of the aircraft with respect to the wind that is there, the airflow that is there. That airflow, even if you assume, let's say, there is no, let's say, wind, then you still have the aircraft is moving in a particular direction. You will have certain differences. But once the wind sets in, that is also going to further complicate. So just like we have an E system, you have a B system, and you have a H system, H standing for horizon.
Are you referring to local horizon in this?
Yeah. That's correct, yeah. So in addition to the local horizon, you will also introduce a wind fixed coordinate system, because then you have a velocity of the wind, which direction we will call as the x direction, and then you will have similarly perpendicular to that, and you will have the xyz system associated with that, which we will call as the x w, yw, and zw. Okay. How these are distinguished is once again to retain your xw plane of symmetry. So you will ensure that that continues to remain a plane of symmetry. In other words, the overall velocity that is there may not be parallel to any one of these directions. It's actually along the xw by definition, but when there is a disturbance, that could change along, have components along the y and the z direction. And in fact, the induced drag that we talked about, one of the actual explanations to go about that is because of the downward, or what we call as the downwash, that is actually happening over there, right? Now, so these are the four systems of unit vectors and reference frames that we will be using pretty much for the entire portion of the 3D degree of freedom system derivation of the equations of motion, and they will help us with respect to the 6th degree of freedom system, 6 governing equations of motion as well. So it's very important to understand them, and it's fairly straightforward and simple in terms of how they differ from each other. Let's start with the Earth. Going to the local horizon system, you have only a translation, absolutely no rotations. Then you're going from that to, let's say, the body. Then you have what is known as the flight path angle, which is coming in place. In other words, if I draw a horizontal over here, the angle between the horizontal, which is the local horizon, and the xb is what we call as the gamma, denote by gamma, and call it as the flight path angle gamma. Okay, so there's only one angle which distinguishes between the H system and the B system. Similarly, when you're going from the B system to the XW system, there's only one thing which distinguishes it, which is essentially the angle of attack, right? Alpha, because that's by definition the angle which XB makes with your velocity vector. So that's essentially your angle of attack that you're going to have, right? Again, I've drawn this in terms of the velocity of the wind, but equivalently it can be drawn as the velocity of the aircraft opposite to that. So, which means that your XW will actually be in that particular direction. So, we'll use it the way it is convenient for us as we go forward. But essentially, you're having from E to H no rotation, from H to B only one rotation, which is gamma, and from B to the W system only one more rotation, which is alpha, and both these are about the x-axis that you're essentially talking about, right? And in the plane of symmetry. Okay, so is this clear? So because these axes we're going to use quite continuously, yeah. All except for E system, everything else is having an origin at O. Okay, so even though I've drawn it here, it's actually moved over here, and also the direction of the x will actually be in this direction, where it's the direction of the velocity of the aircraft, CG. XW. Yeah. Yeah, so that is to maintain that plane of symmetry that we are talking about. So we want to ensure that that continues. So for because to start with, we'll be deriving only the 3 degrees of freedom system for the particle, and therefore what we will be doing is we'll be treating only the motion in the plane of symmetry. So which means all of these J that you're looking at, JE, JH, JB, and JW, the unit vectors along the corresponding y-axis, tangential to the y-axis, will all be equal to each other. Okay, so only the x and z axis, or the I and the k unit vectors, will be different for these 3, and even those will be same for the Earth and the horizon.
Sir,
yeah.
won't the local horizon change once the aircraft is flying past, or we are assuming that the distance traveled is relatively less.
Yeah,
So,
yeah, a very good point. So essentially, for example, if you're looking at a long range aircraft, obviously the flat earth model essentially doesn't remain any longer, but most of these things are equations we are looking at instantaneously, which means that it's a fairly short duration. So at that location, yeah, about which the aircraft is flying. We might take a delta t around that, but eventually we will always be shrinking that delta t to 0 in the limit, and therefore it really doesn't matter. Because all of the utility is from taking the time derivatives, first or for velocity and second for acceleration, etc., which you know that the derivative is defined with respect to limit as delta t tends to 0, which means that at the speeds at which the aircraft is moving and the size of the earth, a flat earth model is good enough. So a local horizon, you're right. Anything else, anybody? So let's... Yeah, so that's as far as, yeah, and also as I mentioned, a right-handed system, many times it's referred to as the Dextral system, which is analogous to it. So both essentially mean the same. They're synonyms to each other, right? Coordinate system, and we always take anti-clockwise positive, which is also what we are talking about as the right-hand thumb rule. Another way of saying it is anti-clockwise, and you can very easily verify that's what the positive roll is, the positive pitch is, and the positive yaw is. Okay, so now that with those sets of axes that we have defined and the unit vectors as well, we are ready to go from the 3 degrees of freedom that are there to the 3 equations of motion, which is what we will do over here. And in fact, the utilization of the plane of symmetry means actually we'll have only 2 equations each, because the y gets separated. Because once you have a point mass, as I said, there are no rotations, right? And if there are no rotations, it's only position. So you have x position, y position, z position. Now the y position is going to be separated out from the x and z positions. It's going to get decoupled. So only the x position and the z position is going to be of significance to us, okay? And the z position requires us to define what are known as altitudes. Okay, so there are many ways in which altitudes are defined, especially in flight dynamics. So we will take some time, probably in the early part of next class, to look at the definitions of altitudes from various perspectives. So what we call as the absolute altitude, the geometric altitude, the geopotential altitude, pressure altitude, density altitude, the equivalent airspeed, the true airspeed, etc. So, so those of you with an aerospace background might relate to these things, but we will introduce those terms also in the next class so that everybody else can follow it as well. So now, because of that, in fact, the 3 degree of freedom system breaks up into a coupled system of 2 degrees and a decoupled system of just a single degree, which is along the y-axis. But then eventually we'll bring in the rotations, and then we will see that what was just separated out completely, the y will actually be involving a rotation, which is the roll and the yaw as well, and that will be taken into account. Yeah, so generally the rigid body in 3D space implies 6 degrees of freedom because you have 3 translations and 3 rotations, but its mechanics is therefore described by 6 equations of motion. Because if you have 6 unknowns, you need to have a set to completely solve for them. You're going to have 6 equations of motion, which are all going to come from your 3 applications of the Newton's laws, second law, and the Euler's equation for the 3 moments and the rotation. And once we have a combination of that, we will have 6 equations of motion to deal and determine the 3 translations and 3 rotations. Okay, right. Now, in terms of the equation, we already introduced this, but very important once again to remind ourselves, these are valid only in inertial frames of reference. So there is no such thing in reality as an inertial frame of reference, but we can have a reasonable approximation from an engineering perspective, and therefore we treat the Earth fixed frame of reference for atmospheric flight as a reasonable inertial frame of reference. It will not work when we go to orbital mechanics, etc. We'll take a call over there when we get to that. Then the Euler's law, again, because it is essentially a generalization of this from translations to rotations, from forces to moments, from the masses to the inertia, both products and the inertia tensor, essentially. And then you're talking about acceleration and translational acceleration and angular acceleration. So this is also valid only when you have a inertial frame of reference. So some of these we have covered already, but we'll just state it for completeness. So these are reasonable assumptions that you take for typical aircraft flight and the Earth's atmosphere. So first thing is that the Earth is flat. As he pointed out, it's for a very small time duration. Therefore, the local horizon is all that is of significance there. So we can deal with Earth, even though we know that it is curved surface. We are treating it as a flat surface. We are neglecting the rotation, we are neglecting the revolution, we are neglecting the precession, and then it's also considered to be an inertial reference frame, so that we can apply those two equations that we saw. And then we also make an additional assumption that the rotation rates that we are talking about, either the rolling rate or the pitching rate or the yawing rate, these are all fairly small. So that will kind of simplify some of the things that we deal with quite a bit. Then also we talked about the three control surfaces, the elevators, ailerons, and rudder. So all these control surface deflections, including of course the others like flaps, spoilers, and slats, etc., have negligible effect on the total forces on the aircraft, because the total force of lift, drag, etc., yes, they get modified, but the percentage by which they get modified is not much, because most of these control surfaces deflection is to generate a moment rather than a force. So the force itself, the total lift will not change just because you're increasing or decreasing the horizontal tails lift a little bit by the elevator deflection in order to have a pitch nose up or nose down kind of a moment, right? So it's the large moment arm of where the horizontal tail is with respect to the CG, which is helping us generate a large enough moment to make a change in the orientations that we desire, right? So therefore, this is again something that we'll probably be neglecting as we go. And of course, there are also more advanced versions where we can, without making some of these assumptions, we can still make the derivation. So it's not that it cannot be done. It's not, all of these are not necessary. Just to simplify things to start with, we can make these assumptions in order to apply the Newton's laws and the Euler's laws. So above assumptions imply that the translation equations get decoupled from the rotational equations, because we are treating it as a point mass now, where there are no rotations at all. And then eventually we'll bring in the rotation as well. When it's a 6 degree of freedom system, everything gets coupled, right? So you solve the equation set independent for 3 translational degrees of freedom, and that's what we refer to as 3 degree of freedom equations. But as I said in the books, sometimes what is referred to as 3DOF might be quite different. Instead of treating the aircraft as a point mass, in the regular set of 6 degrees of freedom system, you know that there's a decoupling happening between the plane of symmetry motions and the out of plane of symmetry motions. So each of those is a 3 degree of freedom system as well. So make sure what exactly they're referring to before kind of comparing with what we are doing in the class here. Okay, so we're pretty much following John Anderson's way of approaching this. So if you have any doubts, you can always refer to that book as well. So longitudinal planar motions decouple from the lateral directional equations anyways. So that is what would be 2 sets of 3 equations that I already talked about, even if you're not dealing with the aircraft as a point mass. But what we will be dealing is as a point mass. Okay. So now there are certain additional conditions. Some of them can actually be follow-ups.
This lateral and the longitudinal, how this decoupling will
Okay, very good question. So essentially, when we derive the total set of equations, it's essentially the plane of symmetry. So what we are saying is that whatever happens in the plane of symmetry should not get affected by what is happening out of the plane of symmetry. So in other words, that is a physical argument. But you would see that when we mathematically derive, what actually happens is that the dynamics are such that you get three sets of equations which will not have the rolling, the yawing, and the side slip. And then you will have another set of three equations which will not have the x motion, the z motion, and the pitching, right? So automatically they get segregated out. But you can use physical arguments also to explain that this is a plane of symmetry. So what happens within the plane of symmetry should not get affected by what happens out of the plane of symmetry. Okay, it might look a little hazy right now because we're not actually looking at the equations, but when we and even when we derive the 3 degree of freedom system, again it may not look very clear. When we go to the 6 degree of freedom system, I think you'll be more satisfactorily answered about that. Yeah. Yeah.
This in plane of symmetry, until unless we are considering pitch motion, it will be in plane of symmetry. But once it comes, let's say yaw motion,
yeah,
it will not be in that. Means one thing is there that we can consider only one motion at a time, then it can happen. But say if we have two motion at a time,
yeah,
then how this decoupling?
No, even when you have all these motions at the same time, you will still see that there is a decoupling which is happening. Okay. So it doesn't appear very clear right now when you're talking about, because of the fact that the plane of symmetry that is there, of course there can be small disturbances like what I was talking about, like in terms of the load that you have on either side, there are small fractions. Those disturbances can cause couplings, but they are very weak couplings. For the major portion of determining, let's say, the aircraft flight, you need the forward velocity, you need the vertical velocity, you need the side slip, which is usually fairly small, and then you need the three rotations, the pitch, the yaw, and the roll. When you want to calculate these and their rates of motion, which is the velocities concerned or the angular velocities, then you would see that the coupling, whatever might happen even because of small loss in symmetry that is there, will be very, very small. Okay, so it's essentially from the mathematics you will see that the decoupling happens. Yeah, but again, even when we go from a point mass at the CG to the 6 degree of freedom rigid body system, we are still not having the flexibility of the aircraft. So aeroelasticity is what you have to go to in order to really understand the deflections that are taking place. You know that visibly you can see the tip deflections of these kinds of aircraft, how large it is, and therefore even though it may not be close to the material failure limits, it will be fairly high levels of deflection that are happening and rotations that are happening from a structural point of view. So all of that is going to fairly complicate, and the real situation, a lot of this simplicity that we are talking about will be lost. But what we are interested in is understanding not only from a class perspective in simplifying, but even in terms of the leading order terms. What is going to be majorly dominating the description of the motion of the aircraft? And in that sense, this decoupling always happens, even when, as you said, a complex situation where you might have motions out of plane. Okay, so yeah, I think that's kind of covered. I think we will put my. I don't have it. Where did I put my?
Oh, it's here.
Oh yeah, right. So yeah, let's. Yeah, so we have a few additional conditions also for the 3 degrees of freedom system. One of the things that we will take is that the G is constant at 9.81 meter per second squared. So because remember, we talked about this in an earlier class. That the gravitational force is given by, the magnitude of the gravitational force is given by gmm by r squared. So this is essentially nothing but your acceleration due to gravity, right? So now when you're talking about this r, you're talking about the distance of the aircraft CG from the center of mass of the earth. right? And because the Earth's radius is 6,400 kilometers approximately, 6,371 or whatever, depending upon, again, the location, because you have an extra bulge at the equator and it's slightly flatter at the poles, and in between, again, the various surfaces that are there on the Earth, right? So now when you're talking about that G, the ratios at two different altitudes, let's say at the surface of the Earth and at the cruise altitude of 10.5 meter per second square, 10.5 kilometers that you're essentially looking at, what you're looking at is, let's say, a 6,371 divided by a 6,382.5 squared is the difference in terms of those ratios, okay? So because of the large 6,371 that you have of the Earth's average radius that you have in kilometers, and the 10.5 or 11.5 kilometers that you have added for the cruise altitude, that ratio that is going to affect the gravitational force, whether you take it as constant or not, is not going to make much of a numerical difference, which is why we typically take it as whatever it's at the Earth's surface, we take it that to be 9.81 meter per second squared approximately, right? Then the next thing is that to start with, we will not have any winds. So in other words, there's no turbulence as such, and also in terms of the speed difference, it's only with respect to the Earth. Whatever the speed is there, you will have the same speed with respect to the wind. So the atmospheric properties vary only with the altitude. It doesn't vary with anything else. And then you have the conventional aircraft with fixed engines and aft tail. Like, for example, the last class we had, thanks to him, few military aircraft, MI, and there you actually see that the MiGs that were there can have thrust vectoring, for example. So in other words, you can actually have the, even though the engine as a whole might be fixed, you might have the nozzle thrust vectoring, or the in some other means you're essentially trying to change that. The case which is probably the biggest example for that would be tilt rotor systems, like in a V-22 Osprey, for example. Something which is having a forward disc can become a vertical disc. So in other words, you're going from a propeller mode to a helicopter rotor kind of a mode. So when you have such things, that is going to bring in additional complications as well. Not that it's not tractable, but just that you need to account for those differences, and that's what we will try to do in terms of more advanced courses. But here we will keep it as conventional aircraft where the engine is fixed, and so is the aft tail as well, right? So of course there will be an elevator, and of course you can have an all-moving tail that is there. In other words, the entire horizontal tail becomes like an elevator, right? Now the symmetry that you have, we saw that in terms of the coordinates that we introduced, it's essentially in the XB ZB system. That's the plane of symmetry. Then you have the aircraft modeled as controlled variable mass particle. So in other words, because we want to treat it, treat only the translations to start with. Of course, the angles will be included, but we will see how to kind of do both simultaneously. But because what we are dealing with is not just any ordinary mass, but something which is having certain control variables, and those control variables will include not only the angle of attack, for example, but also, let's say, the throttle. What is the throttle condition that you have? Because the power that you give to your engine, what is the RPM at which you are having the rotations that are happening, which could be a certain fraction of the maximum that is possible or permitted. So based on that, again, the throttle level and the angle of attack, which are control variables, you are dealing with that mass particle that are there. So it's kind of not a typical point mass or a particle that you deal with in a regular statics or dynamics course in the undergraduate level, but a little more complex than that because of the involvement of those control variables. And all the aerodynamic forces, of course, truly speaking, it's only the weight which acts at the CG. The aerodynamic forces act at the aerodynamic center, but when you are bringing it all into a point mass, then in other words the entire aircraft is at the CG, then obviously this particular statement becomes valid over there, that all the forces that are there, whether it is propulsive or aerodynamic or gravitational, they're all acting at the same point because they have to act on the mass that is involved over there. So this is what would be the set of conditions based on which we will look at the equations of motion, just 3 equations of motion. But as I said, because of the symmetry that we have, only 2 variables will remain, which is x and h. So in other words, we'll have 2 equations which are kinematic in nature, only describing the motion without the cause, so that is the force. Then we'll have 2 equations which will be describing the dynamics. In other words, the causes, which are essentially these forces, and how that impinges on the actual motion within the plane of symmetry. And then eventually we will bring in the control variables as well to show how the throttle level and the angle of attack will then affect the forces and therefore the positions and the speeds as well. So all of that we will try to do in the maybe not in the next class because we'll have your presentations, but we'll try to initiate that towards the end of the next class on Wednesday. Okay, thank you very much. If any of you have any doubts or questions related to either what we talked about today, you can feel free to walk by here and ask me, or if you have any questions related to your Wednesday presentations or the report that you have to submit, feel free to ask me. Thank you. Oh yeah, so keep the papers and I would urge you, if some of you have not already done that, to look at some of John Collins' videos. John Collins is the world record holder for paper airplanes. Okay, so he's a great aerodynamicist as well. He understands the aerodynamics. It's not just his skill. Of course, he has a lot of skills, having practiced origami for almost a decade or so. But still, he combines that art along with an understanding of aerodynamics. You will have an understanding, for example, of what is this, why is the wing actually tilted a little bit upward over here, what we call as dihedral. Some aircraft will have it downwards, which is anhedral. And also the elevator deflection, etc., what it actually does in terms of a glider, because a paper aircraft eventually is a glider. So you're essentially giving it an initial thrust, a certain momentum, and then it has to utilize that momentum in an efficient way, either to maximize the range or endurance or whatever. And a lot of these aerodynamics that looks fairly complicated when you're talking of an aircraft looks much simpler when you're dealing with an paper aircraft, and it's much simpler, economical also in terms of making changes and trying to see what exactly happens. So sorry we didn't use the papers, and also we had another voluntary effort that will also get postponed. We will have it either in Wednesday's class or Monday's class. Okay, so a small demo by the group captain which kind of makes us understand what I just talked about in terms of the dihedral, etc. Okay, so thank you very much. Those of you who want to ask me questions are most welcome.